Hello everyone, welcome to tutorial 11 for the course CCE 457A. So in this tutorial we are going to review a specific algorithm in reinforcement learning, well specifically deep reinforcement learning, and that algorithm is DQN, Deep Q Network. So deep reinforcement learning is the summation of deep learning and reinforcement learning, where we integrate deep learning into the reinforcement learning paradigm, and that will be the deep reinforcement learning. So the algorithm, as I mentioned before, that we want to review here is DQN, Deep Q Network, which is a value-based off-policy model-free TDRL algorithm. So remember that last time we reviewed Q-learning, and this time we are going to study Deep Q Network, but we are not going to dive deep into the deep learning stuff of the deep learning part of the DQN. It's only an introduction to DQN. So DQN, as we know, Q-learning can struggle with situations when the number of observable set of states is very large. So when we have a large number of states, so you can remember that in Q-learning we had a table for Q values, for rows of states, and columns of actions. So when we have a lot of actions or a lot of states, Q-learning can struggle in these situations. So we need another algorithm for that. In this case, DQN algorithm is a model-free online off-policy reinforcement learning method that instead of the Q table, Deep Q network employs a neural network as a function approximator in order to, so that function approximator acts as the table and gets the value for the states and the actions, and produces an action value for that state and action. So instead of having a table, here we have a function, and a neural network or other networks in deep learning can act as that Q function. So they can use CNN, they can use LSTM instead of a simple neural network. But here we are considering this simplest network, a 1-layer, 2-layer, or 3-layer neural network that plays the role of the Q function. So DQN can handle both discrete and continuous observation spaces. It means state spaces, making it more versatile than traditional Q learning. Okay, so why are we using a neural network, a feed-forward neural network as the function, a Q function? This is due to the universal approximation theorem that states a single layer neural network, like a feed-forward and with a single hidden layer that contains a sufficient number of neurons, can approximate any continuous function on a compact set of the input space to arbitrary accuracy. So this means that a neural network with the right architecture and a large enough number of neurons can approximate any functions. That's the reason we're using a neural network instead of a table in DeepQ network. So for DQN algorithm, we need to train that neural network, meaning that we need to minimize a loss function in order to find the parameters of that neural of the neurons of the weights in that neural network, the weights that connect the layers. So we need to find the best value for that for those weights, stated here as theta, for that function to act properly, to approximate properly. So in order to do that, we need to minimize a loss function. So this is the loss function that we are minimizing. This is the loss function used in DQ network. So as I mentioned previously, you don't need to uh, worry about this stuff. Well, if you're interested in deep learning and deep reinforcement learning, the references that come at the end of the slides can help you in this regard. But this is only a simple review and introduction to deep Q network because deep learning is not covered in this course. So this is the steps of the algorithm for DQN. You can study that yourself. So here the problem is a grid world problem that we want to apply DQN to this problem. The goal is to train a neural network that plays the role of the DQN agent. And the grid world is designed such that any move that does not win the game receives a reward of -1. The winning move receives a reward of +1, and the losing move receives a reward of -10. So what is this grid world? This is our grid world, a 4x4 grid. A represents agent, or they also show it by the by the letter P, meaning player, and W is wall, negative is pit, the where we lose, and this is our goal where we win and get a reward of +10. So any moves here produces a reward of -1. The move that or the action that leads us here in this part, pit, gives us a reward, gives the agent a reward of -10, and the move that leads us here produces a reward of +10. So you want to train the agent, the DQN network, so that agent can find its own way to the goal. So this is the game state, and this is the neural network, like a neural network with 2 hidden layers. This is an example. So the states here are the input to the neural network, to the Q function. These are the hidden layers, the weights of which we want to find, like the weights connecting the input layer to the first hidden layer, the weights that connect the first hidden layer to the second hidden layer, and the weights that connect the second hidden layer to the output layer. And the result is the action. So based on the state of the game, the neural network will produce an output, and that output will be the action, whether for the agent to go right, left, down, or up. All right, so the figures were actually taken from this book, Deep Reinforcement Learning in Action, and the codes that I'm about to show you in Google Colab are taken from this repository, from this GitHub repository for the book. All the codes are available in there, and yes, you can use them. All right, so before moving on, I need to mention that I have uploaded the code here. DQN for grid world in the GitHub repository of the course. And this is also the GitHub repository that I mentioned for the book. So all the codes are here in chapter 3, and you can download and use them. Also, all the codes are described in the book and are very well commented. So if you have a knowledge of deep learning and implementation of deep learning in Python using Torch or PyTorch, there should be no problem for you understanding the codes in this book. All right, so I'm just gonna run the cells one by one and show you the result of the applying DQN to the grid world, and that will be it for this tutorial. Alright, so this part of the code creates the grid board for the grid world environment. And this one is the actual environment, like grid world. And that initializes the board to the size of 4, like a 4x4 grid. We have player, the agent, we have the goal, pit, and the wall. Now we need to create our Q function or DQ agent. These are the hyperparameters. So we have 4 layers. We have the input layer, hidden layers, and the output layer of 4 neurons. So each neuron represents an action, like up, down, left, or right. And we're playing the game in 5,000 epochs. So this part of code creates the Q function, a neural network model, sequential model. Now we're going to train the model. So this training part is where we want to minimize that loss function to find the parameters of the neural network, the weights of the connecting the neurons, the weights that connect the neurons in a neural network by minimizing the loss function. So that's basically training the model. So because it's 5,000 epochs, it's gonna take a while. Alright, so it took the model 2 minutes and 15 seconds to train. I noticed that I'm using a GPU, so it's going to be much slower on CPU. So remember to change that if you want to run this code. All right, now let's plot the results. The results show the loss function in each epoch. All right, now we're gonna test the model to see if the model works properly. And yes, this is the result of testing the model. So as you can see, this is the initial state of the game. Player was here, pit was here, goal was here, and the wall is here. Move number 0 So the player played the right action. So because the right side is blocked, the player stayed in the like in its previous state. After that, the player played up. Then again, the upper block or the up move here is also blocked. So the player stayed in its previous state. Then took it right and blocked, up, block, and up, blocked again, and played a series of up and right. I don't know why, and lost the game because of too many moves. So yes, so the amount of moves are were greater than 15. Game lost, too many moves. All right, let's run that again. I think that will give us the same results. Yes, unless we retrain the model. Okay, so here we train the model, and in 3 steps, the player lost the game. So the first move was left, so the player ended up here, and then the player moved left and ended up here in the pit and got a reward of -10. So game one is false. It means the player lost the game. Okay, everyone, that's it for this tutorial, and you can download the code. And if you understand, if you have basic knowledge of deep learning, you can understand some parts of the code, but it's better to go through the code step by step using the book to understand the code fully. And that will be it, and that concludes this tutorial. Until next time.